Good morning. We're going to continue our discussion of Bodie plots today. So again, this is in section 9.3, Bodie plots continued, and we'll work through a couple of examples. Again, since I'm doing these lectures via video, the lecture will be broken up into several short videos today. So again, you can play these back a little faster than real time. Pause, turn on closed captioning. They'll all be uploaded to YouTube, and take a short break between videos. Um, with regard to Bodie plots, so far, we've kind of looked at you know, two simple forms. A frequency response that may look like this: 1 plus j omega over omega c. This would be called a zero term. Our transfer functions will all usually appear as rational functions with terms like this in the numerator and additional terms in the denominator. When we using the Bodie technique, when we plot the magnitude response of a term like this as a function of frequency, and what that looks like is for frequencies below omega c, we say it's equal to 0 dB. And for frequencies above omega c, we draw a straight line that would continue on forever, that increases at a 20 dB per decade rate. Okay. And some of the examples today will show you how to combine, when you have multiple terms like this, multiple zero terms in the numerator, and then a pole term would look like this: 1 plus j omega over omega c. So the only difference now is this is in the denominator. So when we take 20 log of the magnitude of this, we'd have 20 log of 1, which is 0, minus the 20 log of this term. So it's just the negative of this term in the dB scale. So graphically, we want to just graph the negative of this plot. And so that would look like this: omega here, omega c. Again, it would be 0 for all frequencies less than omega c. And then now it would decrease at this negative 20 dB per decade rate. And then, so using that semi-log graph paper that was handed out last time, it's easy to draw these 20 dB per decade lines when you lay that paper out, when you mark that the axes on that paper appropriately. Again, we'll show you how to do that in some of the examples today. There are some other standard forms, some that are actually a little simpler than this, like just a j omega form. In either the numerator or denominator, or a constant term. So other standard forms are in table 9-2 on page 516. I will make this available for you in PDF form so that you can print this out. Of course, you can print it out if you get the PDF form of the textbook. This will be the reference you're allowed to use for the exam with regard to drawing Bodie plots. Okay, so you will want to study that and be familiar with it, and actually use it while you're working some of these homework problems. So this is what that page looks like. Again, we're only doing the Bodie magnitude plots here, so you don't have to worry about the Bodie phase graphs. But a constant would be a constant on the Bodie magnitude plot. If it's just a constant k, to convert that into dB, it's just 20 log of that value. If you have just what's known as a 0 at the origin, so that's a j omega term as opposed to a 1 plus j omega term. A j omega term in the numerator would just be a line that goes through omega equal that crosses 0 dB at omega equal to 1. Of course, if it were j omega over omega c, it would cross through the 0 dB line at omega equal to omega c, where that ratio is 1 and 20 log of 1 is 0, and then increases at a 20 dB per decade rate. Now, more generally, it might be j omega squared, in which case it would increase at a 40 dB per decade rate, or j omega cubed, in which case it would increase at a 60 dB per decade rate, and so on and so forth. A pole at the origin would just be, a j omega n in the denominator, or a j omega to the negative n term, and then that would look like the 0, but with a negative slope. And a 1 over j omega squared, for example, would go through the 0 dB line at omega equal to 1, and then decrease at a 40 dB per decade rate. Again, that's a 1 over j omega squared term. A simple 0 like we've been dealing with, looks like this. Again, it's 0 dB up until omega c, and then it increases at a 20 dB per decade rate. Now, if that is squared, it would increase at a 40 dB decade rate. Similarly, a simple pole would look like this and would increase at a negative 20 dB per decade rate for frequencies above omega c. The only other types of terms that we'll encounter other than these simple zeros and poles and simple zeros and poles are quadratic terms. And you could have a quadratic form in the numerator that would have to be factored like this. It has kind of the same general shape for the magnitude response. It's 0 for omega less than omega c, but that it increases at a 40 dB per decade rate if the quadratic term is to the first power, or if it's to the second power, it would actually increase at an 80 dB per decade rate. And similarly for a quadratic pole term, a term like this that now is in the denominator, except for frequencies above omega c, it would decrease at a negative 40 dB per decade rate if capital N is to the first power, and then if it's to the second power, it'd be a minus 80 dB per decade rate. So refer to this table as you're doing the homework. You will be allowed to use this reference during the exam. There'll be a link to it on the lecture site for today's lecture. Of course, it's in your textbook as well, but I recommend that you print it out as a separate sheet so that you have it as a handy reference as you're going through the homework. Okay, this lecture will continue in the next video.